Welcome! In this video, we are going to discuss integration by parts. So there is a simple formula of integrating functions that are basically the product of two functions. Now you might be thinking that you've done that through use substitution, but that only works for simple functions. Prior to explaining the formula and doing examples, let's go ahead and derive it first. And to do that, we will need to recall the product rule. And the product rule says that the derivative of a product of two functions, f and g, it's going to be equal to the sum of two products. And what I mean by that is, first, let's go ahead and treat f as a constant, differentiate the second function g, then we'll go ahead and treat g as a constant, differentiate the first function. So this is going to be the essence of where the integration by parts formula comes from. Let's go ahead and integrate both sides of this line right here. So integrating both sides, we're going to go ahead and obtain the following. We're going to do the right side first and then the left. So the integral of fg prime plus gf prime dx is going to be equal to the integral of the left side, and that's simply going to be fg. So now what we'll do, some final manipulations. Let's go ahead and rearrange this equation. And rearranging, we obtain the following. We're going to have the integral of fg prime dx, and that's going to be equal to f times g minus the integral of g f prime dx. So I'm going to use some suggestive notation here, and I'm going to rewrite this formula, but this is the integration by parts formula. All right, so the integration by parts formula is the integral of u dv is simply equal to uv minus the integral of v du. And just to make it very clear, I'll go ahead and box this in. All right, so now we have what we need to do some examples. Let's go ahead and do a first example. So for example, we are asked to integrate the following function. Now, at a first glance, it might look like something we're able to do by means of u substitution. If we let u equal 2x, then du would be equal to 2dx. But unfortunately, that won't work because we have an x factor right here. So this is an example of a function in which we will need to use integration by parts. So let's go ahead and let u be equal to x, and we'll go ahead and let dv equal e to the 2x dx. Now, on the left side, we're going to go ahead and differentiate. So du is equal to, well, the derivative of x is 1, so just dx. And then now to integrate the dv portion, think of the derivative of which function is e to the 2x. Well, in that case, it's going to be v equals 1 half e to the 2x. And let's go ahead and box that in, because this is the work that we're going to use in order to evaluate the integral. So the integral of x e to the 2x is simply going to be equal to uv, so 1 half x e to the 2x, and then it's going to be minus the integral of v du. So simply, well, du is just dx, so it's going to be 1 half e to the 2x dx. And so we'll go ahead and take that one more line, 1 half x e to the 2x. And now think of the derivative of what function is 1 half e to the 2x. Well, from up here, we know that the derivative of e to the 2x is equal to 1 half e to the 2x. So basically, we have this integral would be equal to 1 half of the integral of up here. So therefore, we will have 1/4 e to the 2x, and don't forget your constant at the end. And this is our final answer. All right, let's go ahead and do another example. So in this example, we are going to be asked to integrate the log of x. While many of you will have this formula memorized, we'll use integration by parts to derive where it comes from. So we're going to set u to be the log of x. If you think about it, if we were to set dv to be log of x and we integrated that it wouldn't make sense. We want to differentiate that to get the formula. So then dv, we'll go ahead and set that to dx. Now differentiate the first side, the left side. It'll be equal to 1 over x dx. And then the derivative of what function is 1, well, that's very easy. That's equal to x. Go ahead and set that aside. And we'll go ahead and integrate by parts. So uv will be equal to, well, x log x minus the integral of v du, which is simply x times dx over x. Notice that the x's cancel each other out. So this is equal to x log x minus the integral of dx. And this is going to be equal to x log x. Well, the integral of dx is just x. And we'll go ahead and add a constant to the end. And here is our answer. All right, the first two examples have been fairly straightforward. We decide what u is going to be. We decide what dv is going to be. Differentiate u, integrate dv, and then we apply the formula. What if we can't evaluate the integral of v du? Well, that is where the next example is going to come in. We're going to do this example 2 times. The first time, we're going to apply the formula as we have with the first 2 examples. The second time, I'm going to show you a better method which I typically use for integration by parts. All right, so in this example, we're going to integrate the function x squared sine x dx. So first, let's go ahead and start off by setting u to be x squared, and we'll go ahead and set dv to be sine x dx. Let's go ahead and differentiate u. So du is equal to 2x dx. And think the derivative of which function is equal to sine of x. That'll be negative cosine x. So right here, we're going to apply the integration by parts formula. So this is going to be equal to uv. So negative x squared cosine x minus the integral of v du. Notice that there's a negative sign over with the function v, so we're going to get minus a negative, that becomes positive, so plus the integral of 2x times cosine x dx. And this is how it's different from the first example. We will need to use the method of integration by parts once again for this integral. So now we will go ahead and let u be 2x and set dv to be cosine of x dx. Let's go ahead and differentiate u. It'll just be 2dx. And the derivative of which function is equal to cosine of x? Well, that's simply going to be the sine of x. And this is all of our assigned work, so I'll go ahead and structure that appropriately. So what we obtain is, well, negative x squared times the cosine of x. Now we'll do the second part, minus uv, so 2x sine x. And it'll be plus sign, my apologies, plus 2x sine x minus the v du. So minus the integral of 2 sine x dx. And then we'll do one last 9, negative x squared cosine x plus 2x sine x. And now think the derivative of which function is equal to 2 sine x. Well, really all this is going to be is 2 cosine x. Plus our constant. And here is our answer. All right, so we're going to evaluate this integral again, but we're going to use a faster method. So what I like to do, we're going to go ahead and call this the shoestring method. All right. So basically what we're going to do is notice the way we did it previously, we decided what u was, decided what dv was, and then we just differentiated this side repeatedly, and then we integrated this side constantly. But notice that this sign kind of changes up, so I'll show you what we do for that. So it motivates us, so we're going to differentiate one side, and then we're going to go ahead and integrate the other side. So let's go ahead and do our differentiation first. So x squared is definitely the differentiator. And we're going to take this all the way down to 0. So 2x, 2, and 0. Now we have sine of x. Well, now we're going to integrate. So we have negative cosine x. Then we have negative sine x. And cosine x. Now notice, when we did the previous example, there was a little discrepancy between the signs here. So we're going to take that into account. So let's just make this into a nice little table. So basically, we're just going to take the product of a zigzag pattern here. So we'll take the x squared negative cosine x. Now, we're going to do negative of the second diagonal, and then we'll do plus the third diagonal. So we've got plus, minus, plus. And if you were to do different formulas, you would actually do this exact procedure. So this is simply equal to negative x squared cosine x. Now, minus a negative, so plus 2x sine x, then plus 2 cosine x, plus our constant. And there's our answer. Now we're going to go ahead and do one more example to conclude the lesson. So for example, we are asked to integrate the function e to the x sine x dx. So you can already tell that no matter what we do, we're not going to have this pattern like above where it goes all the way down to 0. So we're going to have to do some sort of manipulation with the formula. So here's how we're going to do it. So we're going to have our differentiation side. We're going to have our integration side. So for the differentiation side, it's always going to be e to the x. So I'll write that 3 times for now. There's a reason why I'm writing it 3 times, and you'll see in a moment. Then we'll have our sine x here. Negative cosine x, negative sine x. So I stop at the third line because notice our original antiderivative is e to the x sine x. The third line, we have again e to the x sine x. This is a repeated integral. Let's draw a little table here. We'll do our plus, minus, plus. So we go first left, second right, second left, third right. So up here, we could have done the integral of 0, but that is just 0. So we're going to end up doing plus the integral of this function. So how would this look nicely? Well, this is how we can write it. This can be written as I equals negative e to the x cosine x plus e to the x sine x, because we have a minus negative. Then we have minus e to the x sine x, which is the original integral. All right, so let's go ahead and just solve this. 2I is equal to negative e to the x cosine of x plus e to the x sine of x. And so our final result will just multiply the right side by a half. So Therefore, the integral of e to the x times the sine of x is simply equal to 1/2. Since the sine of the sine portion is positive and the second one's negative, I'm going to rearrange it a little bit. So 1/2 e to the x times sine x minus e to the x, cosine x plus our constant. And there is our answer. As you can see, if we did the traditional formula method versus the shoestring method, especially for the second example right here, it would have been a lot more difficult. Make sure that you'll be able to see that for a moment. There we are. All right, well, this is how we evaluate integrals by parts. Thank you, and we'll see you next time.